Okay, guys, I said that I would do a um, replacement session here where I cover what I was going to cover in the workshop, but unfortunately that had to be cancelled because of the snow. So, as always, if you want to follow me whilst I do this, then I would recommend that perhaps you slow the video down in YouTube maybe a little bit, just so you keep up with what I'm saying. Obviously, the advantage of this approach is that you can have this video on in the background where you pause and continue as you get to the analyses that I'm about to do. So hopefully, this isn't obviously a full replacement for being in person and having your questions answered by me, but hopefully there are benefits to this approach nevertheless. So to get started, what I want you to do is go on to Moodle. We're just going to open up Moodle here in your browser. Sign in as you would do normally, and go to quantitative methods 2, which is just here. Oops, sorry, it's not that one. It is this one. And then you're going to go all the way down to correlation and regression. Click on workshop materials. Let's open the workshop data set, which is here. While this loads, I'll let you know that there are a couple of things in these materials that I'd like you to use and print off if you can. If you're keeping a portfolio, print them off for that. The first is the dataset key, which essentially this is the same dataset as we used last week when we cleaned the dataset and we worked through imputating the missing values and getting rid of the identifying and getting rid of the outliers. So this is exactly the same data set. All I've done is on the end of this data set, I've calculated the variables by taking a mean of all of the items, which is the last thing we did in the workshop last week. So essentially, what I've done here to calculate these variables is the task orientation, ego orientation, and 4 measures of engagement. I've just taken each of the variables, let's say task orientation. So you've got task item 1, task item 2, task item 3, task item 4, task item 5, task item 6, task item 7, and I've just added them together and divided them by 7, taken the mean value for the items, and then created a new variable with the average score. The task did the same for ego, did the same for confidence, dedication, big confusion. So what we have here is a data set which is essentially the ultimate finishing point from last week's session. Just to remind you, these are psychological variables that are collected in real data that was about 5 or 6 years ago now, when I was doing some work in the area of motivation and youth sport engagement. So these are young youth sport participants, and we asked them why they're motivated for sport. So we asked them some task questions, whether they put a lot of effort in, whether they played sport to learn skills and develop, or alternatively if they were what we call ego orientated, and that's where they play sport for the outcomes, to win, to beat other people. And then we're also interested in a couple of aspects of their engagement, so how confident they were in sport, how dedicated they were to sport, how energetic and vigorous they were in sport, and how enthusiastic about sport they were. Now, the hypotheses that we had was that task orientation would be positively correlated with engagement or the engagement factors, whereas an ego orientation would be negatively correlated with those aspects of engagement. And that was kind of at a very basic level what we were expecting to see. So let's do some correlation and regression analysis to test some of those hypotheses. Now, the first thing to do when you have variables like this, that you're interested to know the relationships, is to essentially just pull up a very straightforward and simple correlation matrix. And a correlation matrix essentially gives us all of the correlation coefficients between each of the variables that we have in our data set. And it doesn't tell us anything about prediction. It doesn't tell us about how much variance is explained in various outcomes or by various combinations of factors or whatever. It doesn't give us much information about how we can use one variable to estimate another variable. But what it does do is it gives us that information as regards to how well variables co-vary and to what extent they co-vary. And if you remember back a couple of weeks ago when we talked about variance and covariance in the lecture, all we're doing here is getting SPSS to calculate that covariance, which is one of the things that I walked you through when we talked about it in the lecture. So in order to get a correlation matrix, what we're going to do in SPSS is click on Analyze, then we're going to go to Correlate, and then we're going to go to Bivariate. Now, you don't really need any other variables in this data set. All the items I've aggregated at the end. So all we're going to do is highlight the bottom 6 variables here from task, orientation, to enthusiasm, and I'm going to put them over into the variable box. We want Pearson's correlation coefficients, 2 tailed significance, and we want to flag those correlations, so that should be the default. I'm going to click on options, and I'm going to get some additional statistics because they're always informative, particularly these cross-product deviation covariances are quite interesting, and we calculated them by hand. They're needed to calculate Pearson's R, so I think it's good to put them in. Yeah, that's fine, and we don't need that. So what I'm going to do now is click on OK. Once we've done that, once we've got our mean level statistics and our cross products, we're just going to click on OK, and what you'll find is a table that looks something like this. Now, this information here tells us essentially what the relationships are between the variables. So you can see here that the relationship between a task variable, task orientation, ego orientation is about 0.33. You see the sum of squares. Well, the sum of squares is, as we talked about in the lecture, the overall or aggregate variance of a variable. So sum of squares, the sum of the squared differences. You see here that across the diagonal is where you'll find the sum of squares. So the sum of squares to the task variable is 84. That's the amount of variance in task orientation. The cross products you'll find underneath the correlation for each of the variable pairs that you're interested in. So here, task and ego, we have cross products. Some of the cross products, which are 42.14. We have a covariance statistic, and we also have n, which is essentially our sample size, the number of cases that we use to calculate those statistics. So Pearson's correlation, standardized indicator of relationship between two variables. Sum of squares is the variance in a variable. Cross products is essentially the sum of the cross products, and the covariance is the unstandardized correlation between the two. And you find here that if we look across all of the correlation coefficients in the table, that all variables are positively correlated with each other. The task orientation is positively correlated with all the aspects of engagement, and interestingly enough, so is an ego orientation. There's a positive correlation with all of the aspects of engagement, but albeit to a smaller degree. So the correlation table is interesting. You'll find that most studies report a correlation matrix, and it's important for you guys as well when you're thinking about doing each assignment to report your correlation matrix to the variables that you have that you've analyzed. The problem, of course, with the correlation matrix is beyond sort of quite descriptive information about what's happening in the sample. We currently get an idea of what's going on in terms of our focal hypotheses, and that's this question of whether these two orientations predict engagement, or we can use the orientations to predict engagement. So the first thing I'm going to do then is move us on to simple regression, where I'm going to just focus on task orientation and look to see whether we can predict enthusiasm, so levels of enthusiasm in sport from a task orientation. And this is now moving to prediction. So instead of correlation, what we're now going to do is something called simple regression, I click on Analyze Regression Linear. Now, our dependent variable, as I said, was going to be enthusiasm. And our independent variable was going to be a task orientation. So one independent variable, one dependent variable. All we're doing here is looking at simple regression with a task orientation on enthusiasm. Okay, what I'm going to do is check the box that says confidence intervals under statistics, because I think those are informative and we talked about them in the lecture. But I'm going to leave everything else as it is. I'm going to, should we get a plot? Okay, let's also, let's get a plot. So let's put on the y-axis our dependent variable, and on the x-axis our predicted variable, or our as our predicted scores, just a predicted standardized result. Okay, let's not worry about that. Let's not worry about that too much for now. So let's leave the plots blank, and we'll put them in if we need to. Okay, we'll leave everything else as it is, and I'm going to click on OK. So what you'll find here is a simple regression output that we went through in the lecture. So the first output you'll have is a model summary, and remember we talked about the model summary being the overall variance explained dependent variable by the independent variable. You can see here that we have an R value of 0.497, which is exactly the same as the R value in the correlation matrix. You'll also find that we have an R square value here, which is the percentage of variance explained. It's the percentage variance in enthusiasm that is explained by a task orientation. We have an adjusted R square, is adjusted for a little bit of error. You can see here's not much adjustment because we have quite a large sample size, so there's not a great deal of error in that estimate. So essentially all we've really done here is replicated what we did in the step above, but we will come to see the importance of this model summary as we add more predictors into the model. So let's move now to the ANOVA table, and you can see here that we have a number of different outputs. And I want to draw your attention to, first of all, this sum of squares output. Now remember I talked about sum of squares being the aggregate amount of variance in a variable. So the sum of squares for enthusiasm is 85.29. You'll see here that enthusiasm and enthusiasm on the diagonal has a sum of squares of 85.29. That is the aggregate amount of variance that is explained, that is contained within enthusiasm. Okay, the sum of the squared differences of each individual score from the mean. Now we also have in this sum of squares table a sum of squares for the residual. And remember, the sum of squares for the residual is when we plot the points of task against enthusiasm, and we draw a straight line through the intercept and combined means of the two. What we have is essentially ordinary least squares regression. Okay, we're plotting and solving the regression line for the minimum or least amount of square differences between the observed point and the predicted point. So when we solve for those residuals, and when we calculate how much variance there is between the observed score and the regression line, what we have is a sum of squares for the residual. So how much variability there is in the scores around the regression line. And then, of course, if we take the residual away from total, what we're left with is the amount of variances in enthusiasm that's explained by task orientation or the regression line. So if we divide our sum of squares by the degrees of freedom in our model, now the regression model here, we have 1 degree of freedom, we have one predictor. So we have essentially what we call a mean square, which is exactly the same as sum of squares in this case, because degrees of freedom is only 1. And then we have a residual, degrees of freedom, which is essentially our sample size minus the number of predictors minus 1, which equals 255. Again, we take 64 divided by 255, we get a mean square for the residual. And then our F ratio is essentially the ratio between the mean square for the regression and the mean square for the residual. And of course, the larger the F, the more likely we are to have a significant effect. And you can see here that we have a highly significant regression model. That is to say that task orientation essentially predicts substantially meaningful amounts of variability and enthusiasm. So as we move to the coefficients then, hopefully this will become clear after the lecture what these coefficients now mean. You can see here that first of all we have a beta coefficient. I remember I talked about that being the slope of the regression line. So for every 1 unit increase in task orientation is a 0.501 unit increase in enthusiasm. And we can standardize that coefficient here to essentially arrive at a standardized estimate. So for every 1 standard deviation unit increase in task orientation is a 0.497 standard deviation unit increase in enthusiasm. And because these two variables come from the same scale, the standardized and unstandardized beta coefficients are very similar. And also you'll notice that the standardized beta coefficient is exactly the same as R. That's because there's only one variable in this model, and so a standardized estimate prediction is exactly the same as a standardized estimate correlation. Our t-value, remember, is our beta coefficient divided by its standard error. So the standard error, the average squared distance from the regression line, divided obviously by degrees of freedom. And we have here an estimate and a standard error. T ratio is essentially the ratio of these two things. And of course, the larger the t, the more significant. We also have a confidence interval for the beta coefficient that runs between 0.39 and 0.61. And because that confidence interval doesn't include zero, doesn't include a zero effect, then we can say that this prediction model and the contribution of a task orientation to enthusiasm is statistically meaningful. So that's good. What we have here is evidence that task orientation positively predicts enthusiasm. So the higher we are in task orientation, the more effort we put in, and the more we do sport for developmental and learning reasons, then the more likely we are to report high levels of enthusiasm. Now, of course, I'm not necessarily just interested in contribution of task. There might be other variables that we could think of that also influence enthusiasm in sport. And one of those variables is perhaps league orientation. So what I'm going to now do is run multiple regression. But this time I'm not going to include one variable, I'm going to include two. So I'm going to include ego orientation alongside task orientation to see whether task orientation still predicts enthusiasm when the effects of an ego orientation are controlled for, and also to try to understand whether an ego orientation predicts enthusiasm when the effects of task orientation are controlled for. So let's go ahead and run a multiple regression. So we go to analyze again, we go linear regression and then linear. And now what I'm going to do is put my ego orientation here alongside a task orientation. So that now what we have is two independent variables, one dependent variable. And what I'm going to do is go ahead and click on OK. Now here's why the model summary is a slightly different in multiple regression to what it is in simple regression. Because in multiple regression, what we have is essentially an R value and an R square value which reflect a equally weighted or optimally weighted combination of independent variables on an outcome. So some optimally weighted combination of ego and task orientation correlate with enthusiasm at the around about 0.5, and that optimally weighted combination explains about 25% variance. And again, the ANOVA table conveys exactly the same information as what it did in simple regression, but this time the predictors are an optimally weighted combination of ego and task orientation on enthusiasm. But enthusiasm, we see here, still has the same amount of variance explained. The residual is a residual of this optimally weighted combination, and the regression, of course, is just the total take the residual. Again, we have a mean square, we have an F ratio that's large, and we have a highly significant effect for the overall model. But where multiple regression is especially informative is when it comes to interpreting the unique contribution of each of the predictor variables. Because remember, in multiple regression, what we have is something called partial effects, where the effect of task orientation is not the effect of overall task orientation on enthusiasm, But task orientation on enthusiasm, controlling for an ego orientation. That is to say, taking away the shared variance between task and ego orientation, because of course these two variables are correlated, positively correlated. Taking away that correlation from the model, and then using the residual to explain variability in enthusiasm. And you can see here that task orientation is still a positive predictor of enthusiasm when ego orientation is in the model. But what's interesting is that an ego orientation has no contribution to make to enthusiasm here. The beta value is very low, the slope is very low in relation to standard error. Standardized coefficient is very low, t value is exceptionally low, and the significance value therefore is above 0.05, and our confidence interval crosses 0. So task orientation positively predicts, but ego orientation doesn't have any contribution to make to enthusiasm when task orientation is controlled for. And that's really interesting, because if you look at just the relationship between ego orientation and enthusiasm at the mean level, at the aggregate level, you can see here there's a positive relationship. But when task orientation is controlled, that relationship reduces. And that's probably because what's going on here is that those individuals of a high level of ego orientation also do have some levels of task orientation. And those levels of task orientation are probably what helps explain why ego orientation predicts enthusiasm. Of course, when you take those effects away, when you take that residual amount of task orientation away from ego orientation, you find they no longer have an effect, and there's no longer a significant prediction. What's really interesting here is it kind of also is a nice way to explain what's happening in terms of this equally weighted combination of variables predicting enthusiasm in the overall model, because you can see here task has quite a large positive weighting, whereas an ego orientation has a very negligible weighting. And you can see here what that's meant is that there's been very little additional variance explained in enthusiasm from the model previously. So you can see here almost you have to go to 3 decimal places to find any contribution of the ego orientation on enthusiasm when they're put in the model with task, and that's because it's weighted negligibly in that optimally weighted combination. So guys, that's simple and multiple regression, and you can do lots of interesting stuff to demonstrate your relationships graphically. You can build a chart, for instance, in Chart Builder. Essentially, you're going to do a scatter plot chart here where you've got, let's put this one up. So you have x-axis and y-axis. So you might have enthusiasm here, task here, and you can run that. So you can play around with it in SPSS. You can put the regression line through the points like so. We go through the combined means of task enthusiasm and the intercept, and you have the regression equation here. So obviously the beta coefficient times the value of task plus the intercept value, which is 2.36, just around here. And obviously the R square. So you can play around with that if you want to graph it out. It's entirely up to you. But essentially, guys, that's really all there is to it when it comes to simple and multiple regression. Of course, as I said, any questions, as always, do email me, do come and see me if you need a little bit more support in terms of correlation and regression. But all of the readings support the work. And also, I'd really encourage you to go to the correlation and regression checklist, because all of this material and how you conduct this analysis is contained within that document, and you can follow essentially this document to arrive at the same or similar conclusions as to what I've just arrived at. So let's move on. Let's move on to canonical correlation. And what I'm going to get you guys to do here is click on canonical correlation. Sorry, don't do that. Right click on canonical correlation and save it somewhere. Doesn't matter where you save it. It's entirely up to you. But I'm just going to open it up. Oh no, sorry, that wasn't the right one. canonical correlation syntax. Save link as. Okay, so what you should have when you save that is something that looks like this, which is the canonical correlation syntax for this particular file. Now, what I want you to do is highlight it all, okay, and then click run. Don't worry, it's not going to do anything. That's all I'm doing there is loading that particular script into SPSS so that now we can essentially write in the syntax that we need. So what I'm going to do is go into the syntax file. I'm going to pull over the canonical correlation syntax, which is this command line here, and I'm going to move it in. So now what I'm going to do is once I've loaded that syntax in, I'm going to write a quick command which is going to allow us to do canonical correlation. Remember, canonical correlation, multivariate analysis, looking at the relationship between an optimally weighted combination of independent variables and optimally weighted combination of dependent variables. And this is the syntax that you need to write to run that particular analysis. Here, cancor set1 equals task space ego space / next line enter set2 equals confidence, dedication, enthusiasm, vigor space / space full stop, and that full stop is really important. When we run the syntax, what you should find is some output that looks like this. And essentially, this is exactly the same analysis as what I ran through at the end of the lecture when we did a canonical correlation. You'll see here that we've got correlations between sets of variables 1 and 2. This is just essentially the correlation matrix here. Task and ego, remember they were correlated at around about 0.33. This is a correlation between each of the elements of engagement. And these are the correlations between the variables. This is just simple correlation matrix that's exactly the same as what we did here. All right, exactly the same correlations in the canonical correlation output. The canonical correlation, remember, as I told you, was the correlation between the sets of variables. So that optimally weighted set of goal orientation variables, task and ego, and the optimally weighted set of engagement variables, confidence, dedication, enthusiasm, and vigor. So you can see here quite a large correlation, 0.65. And that correlation is indeed statistically significant here. Okay. The second canonical correlation is essentially the correlation between the residuals. So once the relationships are have been extracted and maximized in the first canonical correlation, all the residual variance is then recycled to try to explain an additional factor or additional set. And you can see here that that additional set is also significant. But I want us to focus in this example on this first canonical correlation because it's likely to be the most important. So you can see here the standardized canonical correlation loadings. Important to note this correlation can only be positive, remember, so it's very important we interpret the loadings to get an idea of what's going on with that relationship. Standardized loadings are used to load the variable, the factors, so task, orientation times minus 0.18 into the factor, ego times minus 0.16 into the factor. Same for the engagement characteristics. And then once those factors have been created, what we're left with is something called canonical loadings. And these are essentially the loadings or the relationship, the prediction of the task and ego variables and the engagement variables on their respective factors. So you can see here that this task motivation orientation canonical factor essentially made up of low levels of task orientation and low levels of an ego orientation. And likewise, set 2, so the engagement set is made up of low levels of confidence, dedication, enthusiasm, and vigor. So what that means is that these canonical loadings are telling us that essentially we have low levels of motivation orientation, so low levels of task and ego orientation, and low levels of the engagement factors are essentially going in the same direction. So low motivation orientation, low engagement, therefore a positive association. Now, if these loadings were positive and these were negative, we'd have a negative association. That's to say that one's going up, the other's going down. And if they were both positive, then we'd have a positive correlation. So as one goes up, so the other goes up. So that's why it's important when we're interpreting canonical correlation to interpret the sign and direction of the factor loadings, because they tell us what direction association goes in. And you can see here that in this particular example, what we have is low levels of motivation orientation, low levels of engagement, therefore a positive association. Now, the second set, this other set that was significant, is also quite interesting because this is when the variance that isn't explained in the first set is recycled and then used to run the same process again. And you can see here that what we have when we have a second canonical correlation is low levels of task orientation and high levels of ego orientation. So what we have here is an ego factor, which seems to be negatively correlated with enthusiasm and vigor. Because remember, high ego, positive ego, low levels of enthusiasm and vigor. And that's really interesting because, as I say, once this variance has been taken away from the model, what we're left with now is essentially pure ego, pure task. And it looks like pure ego orientation is associated with lower levels of enthusiasm and vigor. So that's an interesting supplementary finding. But anyway, guys, that's canonical correlation. That's how it's run, and that's some of the interpretation of the output. Now, I do recognize that this hasn't been as good an experience as the workshop, but I hope, having gone through this process, showing you how to run these analyses, you'll at least have an idea now of how to do them. I'm quite happy to make myself available for you, as I said, if you need to come and see me, just to have a little bit more of an idea of what's going on with these particular analyses. And I'm really frustrated that I couldn't give you them in person, but unfortunately there's not a lot we can do about the snow, and booking computer rooms and timetabling slots for you guys is going to be slightly difficult because you'll have very different timetables. So logistically, obviously, we're not going to be able to make the session out, which is why I've done this video for you. But as I say, any questions, please do let me know, and I'll see you on Thursday.